Good morning, everyone. I'm Aung and today I'm excited to share our innovative research on enhancing high-strength concrete using sustainable materials. Nowadays, the global construction industry is growing at 4.5% annually, and which produces 4.7 billion tons of cement yearly. This accounts for 8% of global CO2 emissions. So as we face this environmental challenge, we must ask ourselves, how can we enhance concrete? So in our industry, we need a high-strength concrete with sustainable solutions, and it should be on cost-effective materials. That's why we ask ourselves for challenging questions. How can we enhance concrete sustainability while maintaining strength? So our results present a novel solution by combining two sustainable materials. The first one is refuse-derived fuel, well known as RDF, which is the waste material that we produce every day. Another one is the natural rubber lattice, also known as NRL, which is the natural polymer and we can get from the natural rubber trees, which can enhance the flexibility of the concrete. Here is the here is the ordinary Parkland cement and the materials all we know before. Here is the material properties of refuse-derived fuel, which has the moisture content of 35.2% and mass density of 186.7 kg per meter cubed. Here is the another material, natural rubber lattice, which has a pH value of 10.4 and which has the 52% of dry rubber, and it can produce 0.89% of ammonia. For the moist proportion, we fixed for the water to cement ratio as 0.35 to ensure the performance of the materials. For the NRL, we add 0.5%, 1.5%, and 2.5%. For the RDF, we add 5%, 10%, and 50%. And we test for the compressive strength for 7 days and 28 days. And at the 7 days, we found that the control cost 38.79 megapascal, but surprisingly, our material cost 39.5 megapascal better than the control. For the 28 days, the normal high-strength concrete cost 56.2 megapascal, but our new material cost 58 megapascal, which is a 3.2% increase over control of the high strength. That's why we make also for the density and compressive strength, and we found that optimal performance also at the 5% RDF and 0.5 NRL. And the density decrease with increases in RDF content. Here is for the density and the modulus or elasticity. For the 0.5 NRL, we found that when we add more RDF, the modulus or elasticity will be reduced. But for the NRL 1.5% and NRL 2.5%, we found that if we add more RDF, there will be more in modulus or elasticity. But for the density, if we have 0.5 natural LRL or 1.5 NRL or 2.5 NRL, what we found is if we add more RDF, the density of the concrete will be reduced. And here is the for the substrate cap at 28 days, and we found that the best performance of 0.5 NRL with 5% RDF. For the sustainable solutions, if we use this material, we can reduce cement consumptions, and we can also reduce the waste. For example, normally we use RDF in landfill or something like that, but now we can use RDF in cement, we can use in concrete. It means that we don't need to use too much cement for our construction, and it can reduce a lot of carbon footprint, and we can solve the solutions for our planet. For the performance, we found that our new materials and mixed design can maintain and improve better than the normal high-strength concrete. And one special thing is for the economic visions. If we use RDF and NRL, especially RDF, we can get a low price. That's why when we make a construction, if we use RDF and NRL, the construction cost will be lower. As for the concretion, we can find that we have optimal mid design at 5% RDF with 0.5 NRL, which surprisingly increased 3.2% of the high-strength concrete, and which can enhance ductility and elasticity. And for the sustainable performance, the product can add balance and sustainable performance. That's why for our sustainable solution, using of RDF and NLL can be the driver for our sustainable construction environment. Okay. Thank you very much, and if you have any question, you can ask me freely.